All right, good afternoon. I'm from University of Notre Dame, but I have some Canadian connection, I must. After my PhD, I worked in Toronto at CIBC for a few years in retail risk management, and that experience was sort of a very compelling experience as a data scientist or a data mining professor or a machine learning researcher. There are some lessons I learned working in industry that I bring to fore in my teaching and research as well. One of the things was after I finished my PhD, I thought I was a hotshot machine learning researcher. CIBC wanted to hire me, and I'll go change the world of banking. Lo and behold, how wrong I was. I quickly realized that it's not when applying our skills or whether computational statistical skills to a business problem, it's not about I have the best algorithm out there. It's not about I have the best method out there. It's not about I'll come up with the most complex thing out there. It's about solving a business problem in as cost-effective way as you can and doing a careful cost-benefit analysis on if I implement this complex solution, how long would it take to actually implement on retail risk side or even awarding loans to customers when the branches are all over the country? So one has to think of it from that perspective. And those are some important lessons I learned, which I've sort of, bring to fore in my teaching and everything else as well, and keeping to the point. So just to give you a little bit background about what iCeNSA is, so it's a multidisciplinary research institute focused on network and data science. It's a university research institute, and it's sort of a place where different disciplines co-locate. And to me, that's what we're talking about, whether it's data science or it's big data is, problems come to us, they don't say I'm a computer science problem, I'm a statistics problem, I'm a physics problem, I'm a mathematics problem, I'm an economics problem. It's a problem, solve it, right? So I work a lot with sociologists, anthropologists, physicists, and all kinds of different disciplines. Students from different disciplines actually co-situate in the center as well. So whether it's a sociology student could be sitting next to a computer science student. So that's something which we really thrive and believe in very strongly in iCeNSA. And iCeNSA has been around for the last 7 years now. At the university, that's when I started my tenure track position at Notre Dame as well. And to me, data science is no different, right? We've been doing interdisciplinary research for a long time. We've been doing connecting disciplines, whether we do in bioinformatics or climate informatics or astroinformatics. It's just data informatics now, right? We just have to be, as I like to say, I'm a dataologist, right? We're just trying to understand data, right? From that perspective. So how do we sort of bring those experiences in truly developing a data science curriculum, truly developing training opportunities for graduate students? And the way we work in iSense as a metabolic network is the students and faculty, we are very interested in developing new methods, models, algorithms, and we are funded by a wide variety of federal agencies in the US. We are in the US, but I thought I was in Canada for a second. We have various US federal agencies from DOD to NSF to DOE and a variety of, and what we sort of always insist is in all our projects, we must have an application layer. Whether it's personally, I work on climate change adaptation, I work on healthcare, I work on social networks, I work on environmental change initiatives, work on learning analytics as well, where we look at student e-portfolios and things like that. In doing so, and then we also challenge our students to publish in top high-impact journals or conferences in their own discipline because they're going to get a PhD in computer science or in statistics or in physics, so they have to be recognized as experts in their discipline. But being embedded in an application layer gives them the perspective that I sort of experienced when I went to the bank after my PhD, not having worked, not having had any real-world experience at that point. And whether they are dealing with the real data, whether dealing with the real challenges, and more importantly, they are trying to communicate their findings to bridge two disciplines. That communication is a key. How do we write a paper where that paper would be read by MDs or internal medicine experts, would be read by climate data scientists, or would be read by education experts? So how do we sort of bridge that discipline as well? So it takes a different breed of a student to be able to incorporate and go that extra mile. And as I often say is that, I do a lot of work in healthcare as well, we have a last mile challenge in all of these things. And the last mile challenge is, yes, we'll come up with the best technology. Yes, we'll come up with the best algorithm. How do we actually bridge the gap to make a difference to something, to a person in healthcare, for decision-making in climate change adaptation. Can we bridge that gap? And it's not easy. That's why I love hanging out with anthropologists who sort of, I learn and observe from them on how they study human behavior, how they study societies at a macro scale. And now we're talking about big data and everything else. Yes, I mean, it's really an exciting time to be in data science, and as I say, be a dataologist. It's really exciting time because we now have all this data available. I remember when I started my PhD in 1997, and the data set I had to go download was IRIS data set from UCI repository. Lo and behold, that was our first data set we used for a machine learning 101 class, or PMI Indian diabetes data set, only 150 examples or 800 examples, and those were the kinds of data we dealt with. Nowadays, the students, even high school kids, are spoiled by all this data that's available online now. And so what kinds of questions we can ask? Only our curiosity is the limit. And we can health, scientific discovery, health, dynamics of human behavior, and there was a comment made earlier today as well, is I may tweet something and I may tweet something else later tomorrow, which may completely conflict my first tweet, for example. So how do we sort of truly understand what does it mean from a dynamics of human behavior? We have access to the data. We have access to resources. Computing is cheap. And we'll soon have access to Watson Analytics, where we can throw in and exploit the computing prowess of Watson, even within a cognitive computing context. So, I didn't know there were 12 V's of big data as well, or 6 V's or 4 V's. So, yes, it sounds cool to have these 4 V's, but to me, it's, as a traditional machine learning data mining researcher, although now data science is just a cool, sexier term now, so we use data science, but let's face it, we are data miners or machine learning people to start with. We have volume and velocity. Massive data, streaming data, as I like to think of them. My PhD dissertation in 2002 was learning from massive data. I should have called it big data, would have been the most downloaded dissertation. But the thing is, we have been trying to tackle these problems of massive data and streaming data, incremental learning, online learning. We have been addressing those issues for quite a while as a discipline. And yes, sizes, our data is much larger now, but if I go back 15 years ago, we didn't have that much computing power to tackle that bigger data. So there's always a challenge where we are trying to process data, trying to develop algorithms to deal with the size of the data at that point in time. But the key challenge is these 2 V's, variety and veracity, in my view. Even if we just take all of us in the room today and we say, I want each one of you to give me your data about your social networks, about your social media, about your health, about your anything else, your behavioral data, anything else you want to share. Maybe a couple of dozen folks in the room. Volume is not a problem. But think about, can we even develop, even if I can, are we able to solve the variety problem just for 2 dozen people in the room? How do you build that feature vector? When you have data which is so heterogeneous, which has so much modality in it, so just tackling that one issue and how do we start to assimilate data, even of people in the room. There's no volume, there's no velocity issue. That, to me, is the key issue. And the veracity issue as well. I'll talk about it a little bit too. We go out and we are sort of becoming data hogs, right? I always tell my students as well that one has to fall in love with data. One truly has to. But we are collecting data from all these social media outlets where everybody who has an opinion can say something now, right? There's no peer review, there is no such thing, and even Wikipedia has become a data source. How do I trust the source I'm getting the data from? We all are in the mission to go and get as much data as we can to solve a problem, but data comes with different quality, different credibility, different provenance. How do we solve the veracity issue? I mean, these 2 V's are the most fundamental challenges that we have to start thinking not only from a research perspective, but also from the education perspective as well. And what we do today is, we sort of think about a classroom structure, or a curriculum design or development is focused on, let's think about what is a storage and computation fabric. Let's teach the students about everything that we can. Let's teach them about database service and management. Let's teach them about machine learning and data mining. Let's teach them about visualization. And hence, we have created great data scientists out, and prepared students for the employment marketplace or research or to ask the big questions. But I don't think this is what a curriculum needs today, especially the demands that are being posited on data scientists. And we've seen these two things quite a bit. Sexiest job of 21st century and janitor work is a key hurdle to success, right? And this is very true. Even this is, of course, true. But this is also very true, where it is a janitor work, because imagine you're given a project. And of course, folks in IBM experience it day in and day out, but my academic friends, and you are asked to collect data from 50 different databases, data sources in one organization. How do you begin to put that data together? There are quality issues that you worry about. How do you start to forget all the machine learning, forget all the visualization for a second? Let's go back to data 101. How do we do this janitor work wherein you're trying to basically do data wrangling, you're trying to basically see, okay, what's the quality of data? Data is going to be missing, data is going to have noise, all those things that just because we are trying to tackle big data, those things sort of don't go away. So how do we have our students think about those issues? And they can only think about those issues where they are immersed in a domain, where they truly understand what problem they are trying to solve. Right? It's just not, okay, I can give you all the statistical underpinnings about data. You can apply all statistical principles to verify the quality of data, or missingness in data, or the noise in data, and things like that. But it's incomplete, because there may be nuances in that application or the domain that we are working in that sort of become compelling. And I strongly believe that we just got an NSF Big Data grant funded a month ago, where we're going to be focusing on how do we attach a valuation to the quality of data sources and integration in the first place. What I mean by that is, let's say that I'm asking a question of the data. I'm trying to solve a problem, right? Anytime as a data scientist, we have to ask, what problem are we trying to solve? What's the question we're trying to answer? And I go out and I collect data from a variety of different sources. All data is not made equal. Let's face it. But we treat all data as if they have been made equal. How do we attach a value perspective, a credibility, reliability perspective to our data? So are we teaching our graduate students to think about data from that value and asset perspective? And we've talked about data is an asset, but data is an asset with an option value, right? It's just not an asset. It's an asset with an option value. We have to think of it from that perspective. And then a good data scientist is a problem solver, is curious about data. So if you think about that, yes, a data scientist, we're trying to educate, train, prepare them for the workforce. There's a massive demand for that. It starts with is curious about it as a problem solver. And sort of, these are the characteristics that we talk about the data scientist as a unicorn, and whether that unicorn how many of those unicorns we can produce is a challenge. But maybe it's a team of different individuals who collectively build a unicorn. Maybe that's what the solution is or the end goal is, and that's where building that multidisciplinary perspective to a curriculum becomes interesting. So when in a classroom, do we have students from business, engineering, sciences, arts and letters, all sitting together, each one bringing a different perspective? Are we building project teams in the classroom where the students sort of say, I can bring in this skill set, I can bring in the other skill set? And how do we sort of inculcate that case study problem solving driven mentality in our students? And data science is the process. It is science, it's craft, it's creativity, and it's common sense, right? Some of these things are teachable, some of these things are not. Some of the things some people are naturally gifted with in having that creativity or the curiosity about the data, which, let's face it, we cannot teach. I'm being honest, right? But it's certain things we can teach, right? The craft of doing data science and the science of looking at data. So can we inculcate this process in our curriculum? And the process starts with what kinds of questions we can ask. So I often say this, right? Before we do any data science or any project from an industry perspective or a real-world perspective, not purely an academic perspective, is let's start with this question. If I knew blank, then I could blank, which could result in an ROI of blank. To me, any data initiative in any organization should start with this one fundamental question. And how many such questions we can create to start doing our data science implementations. Because if we don't have a driving question, then we don't know what's success. We don't know what is the outcome we are evaluating on. We don't know what impact it will have. And that's why, if you look at a lot of the reports that came out about the big data hype or myth or things like that, is we didn't quite start with measurable metrics, measurable outcomes for a big project. And if we don't start with that, then at the end of the day, from a business perspective, we go, all right, we spent all this money, we have all this technology, we have all this infrastructure, we hired all these people, but so what? Because we're not accounting ourselves to a question to start with. Can we have our students in a classroom start with that question? And how do we do that? And the way we do it, I do it in I teach data mining to seniors and PhD students, and I teach also a class on healthcare analytics to seniors and PhD students, and sometimes I do machine learning as well. For the class projects, it's team-based, and I ask them to crisply define the problem statement that they're trying to solve. I tell them, this is your own assignment, your class project. I won't tell you, do this or do that. You decide what your problem statement is, and I'll just grade you if you were successful in achieving that problem statement or not. And we go through milestones, we go through a delivery, we have a workshop at the end of the semester where the students make presentations and things like that. But of course, they don't have an ROI or things like that, but I have them start with a problem statement. What is it that, and what I find is students struggle with carefully crafting a 2-sentence or 1-sentence problem statement, because it's not easy. But once they do that and they go through an implementation project in the classroom, they are rock stars. Right? They are sort of riding the wave to be your next unicorns from that perspective, where they have gone through the process and they're constantly going back to what is the problem that we are trying to solve. And that's why I say the data is an asset with an option value as well. Depending on the question I'm trying to solve, the data could have a different asset value to me. It all depends what relevant data I'm trying to bring in from the different databases that I have with me. I think that the business should answer that question. Yeah. Because that's the driver, right? That's the driver of. And data science is the process, right? If you think about what steps we go through, and I think it's a full contact sport, right? We cannot be a data scientist if we are not willing to do the janitorial work of data cleaning and linking. We are not a good data scientist if we're not willing to spend time in truly understanding the domain. What is the data discovery? What is the business process that we are trying to achieve? And then how do you, any machine learning algorithm or statistical algorithm requires a flat featurized data. How do you build a feature vector when data is coming from such different sources with so many different modalities? It's just not about, I'm going to teach my students about analytics, but let's face it, real world is not a UCI data set, IRIS data set, a PMI Indian diabetes data set, or somebody has given you a flat file data set. They have to learn to appreciate how do you create a data set when the data is coming from different sources, even if it's data about a couple of dozen of us in the classroom. How do we build that? And then, of course, we go to modeling and predicting, user interface, deployment, and all the other steps. And these steps are no different than the steps that we are used to, the crisp data definition or things like that. But are we actually teaching our students to really go through this process when arguably this process, until featurizing of the data, takes about 60 to 80% of any data science project? We are focusing a lot on this component here, or maybe this component, the user interface visualization, because we get data which is flattened out already. But if we truly want to create a workforce that's going out and tackling these challenges, are the students getting their hands dirty and going through the pain of what it takes to do this? Right? Are they prepared for that experience from that perspective? And it's also very collaborative, because it's the business and data science, and this is where I think IT typically has been siloed away from business. Data science cannot be siloed away from business. Data science teams and business have to coexist, have to cohabitate, have to co-situate. They have to believe in each other because it's an iterative process. It's not that, and the project is never done. It's not that I'll implement this database and the project is done. Data science project, in my experience, it's never done because you're constantly learning. It's a feedback loop. You take a decision, you run an experiment, you run a direct marketing campaign, you go back, oops, it didn't do as I hoped for this market segment, you go and revise. And you go back and do it again. It's a constant iteration. What Netflix does very successfully with the Kevin Spacey House of Cards, it basically figured out from data what kinds of things people do and ran an experiment with House of Cards. What Amazon does, also it's a constant process where you're constantly learning, you're iterating on what we are trying to do. And collaboration is a key. I mean, I can't stress enough on collaboration between the business units and the data science units and how it could be embedded from that perspective. So the way we sort of do right now in my classroom, talking about training of these is, I have a set of driving applications, whether it's Smarter Health, Smarter Planet, from a different, and what we also do is I invite different companies to sponsor challenges in the classroom. So right now there is 3 different companies sponsoring challenges in my classroom. The students are not required to take those challenges, and the companies sort of give away, have a prize ceremony later. They give some awards to the best projects. That's completely independent of the class. My grading is independent of what they do from that perspective, but it brings them to speak to the students in the classroom. It allows them to present the problems that they believe are compelling from their perspective to the students in the classroom. And the students may choose or may not choose to work on those data projects, but it sort of starts to build that ecosystem. And then I structure my entire curriculum. It's a sort of a very non-linear way because the textbooks typically focus on one thing or the other thing, so I don't use a textbook. I structure my curriculum in that process of how do you get the data, how do you do data understanding, how do you do quality stuff, how do you ask the questions, how do you posit hypothesis, how do you discover hypothesis. Then I talk about modeling, and I insist in my data mining class as well, it's just not about you being the best machine learning person. For that, take my machine learning class next semester. But in this class, it is about, are we thinking about the data? Do we have that perspective about data, that outside-inside view about data from that perspective? And so this has really worked as a model in the classroom because the students have gone out and done quite well, and a couple of students have, we publish papers from the class, students like research papers, they publish in top places. A couple of students have actually gone and started their entrepreneurship, spun off companies based on their class projects from these classes because they really were thinking about what really excites them and appeals to them from a project implementation perspective. So that's where I think a thing which I have learned is it's very important to make the project, the implementation, as the strongest thread in the class, where the students actually do the entire hands-on through the classroom. And something else I do from a computer science perspective, I think I bemoan the fact that we don't do enough case studies, which I really applaud the business school to do. And computer science, we don't do case studies. And I think it's very important, even for when I was in the bank, I realized I had to do case studies. I had to do case evaluations. And I was a computer scientist PhD. Why should we not have our students be exposed to that level of thinking? Because doing case studies imposes a very different kind of a thinking and approach. And in the entire class project experience, the students even conduct single blind peer review of each other's papers. They give feedback to each other. We have a workshop at the end where they present. And more importantly, they are the challenges that we are trying to impose on the classroom from these industry partners make it a very nice experience. So what I'd like to build out of all of this is, yes, we have Kaggle for data science challenges. It's a fantastic place to be. And it gives a great opportunity to download data sets for the classroom. What is missing is, in Kaggle, we get the data set, we report performances, but we don't experience what's the experiential learning of data science process. Nothing is disclosed there. We don't go through that process as to, we get these data sets, we do this integration, we do this quality, we do this. The students are not quite going through that experience, even on a Kaggle challenge, where the companies have given data set, You go download that data set and you try to come up with the best machine learning algorithm or statistical method you can to win the challenge. And you try to get 80% accuracy, 85% accuracy, 90% accuracy, whatever the benchmark is. But in doing so, we are not teaching our students the 60% or 80, 70% of the time that's spent on getting data, cleaning it, doing quality analysis, putting it all together. So can we not build a web portal wherein that kind of experiential learning can be put together? Where companies, instead of saying, here's my data set, take it, say, here are these 4 different data sources, now go through the process and experience that. So it really requires a significant public-private nexus. Like I have access to a ton of data set. One thing which I do is I'm a data hog. I love data, and whenever I see data, my eyes just light up, and I just collect everything I can because data is an asset, right? So we have a lot of public data, and we're sort of creating these scenarios wherein can we sort of start to build out these systems wherein students and different universities can cultivate and participate from that. And then maybe we can build a data science ecosystem, and the Concordia International School in Shanghai students could be participating in this from China, or students in a school in India could be participating, a school in South Africa could be participating, and the level difference that we have from that, there was a statistic about how many people we don't have enough skills or things like that. Can we, via this portal, come together to provide that experience to the students, wherein there can be that public-private nexus, which is, in my view, more powerful than taking a MOOC class, right? Because it's not hands-on. This is hands-on, and data science is hands-on. And what we need is somebody who's curious, is a problem-solving skill, has the analytical thinking, mix that intellect with, now learn some machine learning principles, learn some statistical principles, and here's a data set to go crazy about. We have a winner. Right? That's what we're trying to find. And then there's no limit on finding unicorns. There's enough people in the world to find unicorns. But are we doing the right thing and bringing out the right unicorn in front of us? Where it's not just teaching that one concept or the other concept. So that's what we do. So a lot of our research at iCeNSA and the research that I do is, I try to triangulate between research, innovation, education, and service. We have a lot of projects where in healthcare we do a lot of pilots. We have developed some significant algorithms in personalized healthcare and things like that. But we didn't want to stop there. So we're running 4 different pilots in 4 different settings, from seniors to with pregnant women to adolescents to a diabetes population. And the challenge was, yes, we publish these great papers, we're getting great citations. How good they really are. Let's take them to on a test drive. And the students are now, working with focus groups, getting those experiences back from them. And we do a lot of this service-driven research where we worry about what impact are we making to the world? What difference are we making to the society with our research? And there is so much public data available from open data movements, from World Bank, from, Medicare has published a significant data source as well, CDC, et cetera. You can get some sampling of Twitter data. KD Nuggets is a great resource to download other kinds of data set as well. There are enough opportunities to do research and innovation and also do service from the research as well. And maybe that's where the public-private nexus also comes in, is what kind of data sources and computing sources we can put together. What if there was a Watson Cloud instance which would say, let's do this triangulation where we will sort of provide this compute powerhouse, get your data, and achieve the outcome where you innovate and you also solve a global problem or a societal problem. That is going to be very compelling. And that would also worry about, are we, as with any STEM or computer science discipline, how much of how attractive it's going to be to female students as well. And research has shown female students, especially in computer science, get more attracted to a discipline when there's a tangible outcome, when there is some difference being made. So maybe in doing this, we can make the entire discipline also more attractive to female students, that yes, it's just not being, for the lack of a better word, being a code monkey or being a gamer sitting in your dorm room, which is the stereotype male college student from that perspective, but it's actually you're building something together which will have a difference. So maybe we can approach those things. And all these projects that we worry about are on my website. on my homepage, and I'm happy to share more information as well. And also, I'm very happy to share what the development that we've already started to do to build out this data science portal, and would welcome partnerships and collaborations from folks in the room as well. Thank you.